Hello, I think going to keep this short. I didn't really know what was going to be covered up to this point, particularly by Norman Frank. So I've come with without a lot of preparation, just trying to fill in the gaps of some of the things. And there's one topic in particular that I do want to talk about very briefly. I also wanted to elaborate a little bit on what's been said earlier. In particular, there was some earlier talk, I think, between Bob and Vint about why wasn't CSMA used, or why was it one frequency instead of two? And as Norm has pointed out several times in the past, there were a couple of reasons. Of course, one was there was all of this traffic coming back from the 360 computer to users. Users were putting in relatively small amounts of data typically from their teletypes, and then a flood of data coming back from the 360, which didn't want to be competing in the random access channel. And the other very important point was that the TCUs that were first built for the system were hardwired hardware units, as you saw, and there was a strong incentive to keep them as simple as possible. So having the STAR system with those TCU units just sending a packet using the simple random access technique, and then receiving data back on the other frequency was a way to do that. And so that's why that architecture, I think, was chosen initially, and not otherwise to, even though CSMA was an idea that I think correctly Dave Wax had introduced back in the early days of the project, but it wasn't built that way. The other, why am I? Yep. The other point that I wanted to touch on was the gateway and internet, what we have the connection to ARPANET. In a way it was interneting, except that AlohaNet packets only had one address in them, the address of the terminal unit, or later the PCU, and with the assumption being they were going to be talking to the IBM 360. So eventually, the Mini-Uni was in fact rewritten as a version 2 with a gateway in it that allowed users to connect to the satellite channel, to all the different things, the BCC 500 that has been pointed out up here. But there was no destination address in the packet formats. So that was accomplished by users typing in, probably with an escape character. How do I get this to stop doing this? Who they wanted to talk to. Was it BCC 500, 360, or so forth? So it was, and then the Mini-Uni would maintain a connection table, excuse the word connection, for each user as it set up, after it set up the connection for who it wanted to talk to. So it was a internet without internet protocols, if you will. Not sure it would be that, but it did do that. And in fact, the programmable units added additional flexibility, and then it allowed one user to talk locally to another user, again, using the Mini-Uni and a connection table to accomplish that. So just wanted to add that. I'm not going to tell you anything about the programming of PCUs, because I didn't do that. That was Chris Harrison, I believe, who came into the project a little bit later. I did program them in a uni, and it was software. What can I say? What language? PL1? I think it was PL1. In fact, as part of the project's educational benefits for the grad students involved, Wes Peterson, I think, supervised a special compiler that was written for the project, for PL1. Anyway, that's really, I don't have anything else to say about the software. I don't think it's all that terribly important. I think you've heard the important ideas of the original project. But one area that hasn't been touched upon is something that happened around 1972 or so. Not sure exactly how it got going, but there was a flurry of activity in designing a satellite reservation system using Aloha from two or three different sources. And in fact, I think, Norm, maybe you introduced the ARPANET satellite system notes, because you like the acronym, and that documented some of the ideas that were being explored by Norm and BBN, who was involved in the project with us in a peripheral way, coming to meetings and so forth, because it was terrible to come out to Hawaii, but they forced themselves to do it. And that activity led to, by the way, there's a few of those satellite system notes that I found are stored at UCLA in some archives there. Anyway, there were three, I think, notable and distinct reservation systems that were developed. And the problem was here's geosynchronous satellite, quarter of a second delay each way. How can we do something that tries to keep the delay to that quarter of a second where we can, for interactive traffic at least, and otherwise use the capacity more efficiently than the 1/2E or even 1/E. And so the notions of two things were added to what was otherwise would have been assumed a simple slotted Aloha channel for the satellite now. One of them is the notion of a frame, where then slots repeat, with the frame being roughly, for some of the schemes at least, the round trip time, about a quarter of a second, or it could be longer than that. And the other was to introduce a little bit of processing in each of the nodes for distributed processing to, again, not introduce still more delay with the central controller that kept track of things. The simplest there's about three systems I want to talk about. The simplest was one that BBN wrote up called Reservation Aloha, which was very simple, which I would, the simplest of them, I would characterize as grab and hold. You have the standard Aloha contention channel, but if a station is successful in sending in a slot, and that station has more to send, then they own that slot basically for pretty much as long as they want to send it. Now you could introduce some constraints on that, but each station then remembers, marks, has a little frame table and marks those slots that are in use and knows not to use those slots. So once you're successful in getting in, if you have a queue of backed up traffic to send or just a stream of things to send, you can just proceed to send it and you're removed from contention. That improved things a lot for heavy users, and you still had the potential for light traffic, still was using the contention protocol for the other slots. The second scheme we developed out in Hawaii and wrote up with, didn't have too fancy of a name, but it was called basically a reservation TDMA / Aloha scheme, which for this one we would characterize it as bounce the interloper. This took that same frame notion, and now we're going to add some little more complexity to the nodes to keep track of things. Basically, we're not talking about huge populations of terminals or stations. We're talking about, depending upon the channel rate, but for that round trip time of 1/4 of a second, maybe dozens or so. We would use a standard TDMA scheme to assign each slot of the frame successively to each station, which is a fallback when traffic gets heavy. And otherwise, if you want to send, you always start by sending in your own slot if in fact it's available, but you could also send in other slots. What happens is as you send in that slot, in your own slot successfully, as the other stations receive that, you can also piggyback a reservation in there for other traffic that you might want to send. And that then gets put into a queue, a distributed queue that everybody is processing. And so they can start, once a station is successful, they can start using other slots that are assigned by the queue process and have additional capacity. The name of the game here is demand assignment, of course. Now we're doing a little more of reservation-based queuing and assignment. But now what happens if in one of those other station slots that are now being used by somebody, they want to start sending? Well, then they deliberately cause a contention by sending in their slot that somebody else is using. Not greatly efficient, but so that's sort of the bounce them out and then reclaim your system. Now, as the traffic builds up, if you have heavy duty cycles for all of your stations, it in fact has the nice behavior going down to kind of classic TDMA channel where everybody is being treated fairly. But again, both of these schemes have the disadvantage, the first one of a gross lack of fairness, if you will, and of some potentially shutting out other users, and the second one of deliberate contentions to knock people out of your slot. So as a third approach, Larry Roberts wrote up one called, what did he call it? He called it basically a subframe reservation, demand assigned reservation scheme, where he introduced the subframe for contention, short contention reservation packets, which then, as they're received by everybody, would be used in a queue to schedule the slots in the rest of the total frame. And then, and with the nice feature that as loading, depending upon the loading of the channel, that subframe, if there's nobody really using the channel, that subframe could expand out to be the whole frame for Aloha access to make reservations. And this is at the expense now of 2 round trips because now we're demanding that everybody make a reservation to send their data packets. So this is actually, that scheme was written up by Larry Roberts in one of the proceedings conferences, I think, in 73 maybe. All of this happened around 72, 73. And that turned out to be the basis for that basic subframe for pretty much the ensuing reservation schemes. 1 minute, okay. And in fact, as we've talked a little bit about SatNet, this was 1972, 73 that these were being played with. In 1975, I went to BBN in 1975, and we proceeded to program the satellite IMP, actually just an IMP, took it to the initial interfacing to the Spade Channel and Intelsat with a very simple scheme, but ultimately the Larry Roberts basic scheme was used to develop CPOTA, a more general, in fact, just POTA, a more general scheme. Okay, I'm almost done. I'm not using all of my time, am I? Time is up. Okay. Well, I had a couple more things to say, but I do, since I didn't have, I wasn't sure whether I'd really need to say much of anything here, that it would all be already covered by the speakers that came before me. So, if you'll bear with me. And I thought about, gee, 50 years ago, what was really going on? I don't know why, playing with that initial Aloha system, bringing it up and building it around, what, 71 or so, I think, when we actually got stuff going, 71, 72. So I wrote a poem. And if you'll bear with me, this is as I thought back to those days. Ode to a teletype. My Model 33, sitting next to the rack, how stately you looked, front and back, as you told me of packets randomly arriving and of errors occasionally compiling. We tested the scope of the Aloha scheme's worth amid the skeptics' unconcealed mirth. Sometimes a mishap would now and then occur, but the team rose to fix it in a blur, and the channel resumed its operational purr. We didn't know, you and I, it would lead in the future to Ethernet and Wi-Fi and be used in the sky. Now we've come together to celebrate 50 years after the starting date, aging and uncertain of our fate. But my thoughts still go back to the Model 33, standing on the floor in front of me.
I hope you're all having a very good evening. I just want to start off by thanking UC Santa Cruz, Baskin School of Engineering, and Citrus Banatov Institute, especially JJ Garcia Luna for inviting me and putting together such a good show. I wanted to start off by showing a picture of the University of Hawaii engineering building, Holmes Hall. Those of us who went to school there have fond memories. And fourth floor of this building is where all the action took place. Okay, so, and I just wanted to quickly mention that actually during those Aloha days, this is slightly before my time, There's a lot of groundbreaking work was done. It was a mecca of communication theory research. I mean, there was a lot of work done on source coding. There is, of course, a lot of work done on error correcting codes. Professor Shulin is here, Wes Peterson, Ned Weldon. But the most marquee project that came out of UH was the Aloha, which is what we are here to celebrate today. And I was not there, okay? But I came along later. So what I'm going to do is I'm going to describe a series of projects I worked with Norm on. Unfortunately, I didn't have the opportunity to interact with Professor Koo here because he was gone. But I have a long history of association with Norm and Joan, actually. First as a graduate student and subsequently working in a startup company together. So this is going to be a little bit of history, some technology, but it's going to be more history than technology. And I'm actually honored to be in the company of all of you here, but I'm a little bit nervous because all of you seem to know a lot more history and a lot more technology than I do. So I apologize if I get the details wrong. Everybody knows about the connection of Ethernet and Aloha. And you know, Bob Metcalf started a company called 3Com. And you know, most of us of our time know 3Com as a company that was making Ethernet switches, routers, maybe low-end routers. And they used to make something called NIC cards. Remember that? Network Interface Controllers. Those were the days when you go buy yourself a desktop computer, go shop for the best NIC card, okay? So that is what they were building, but that is not how that company started. The company started off by making a bunch of products where there were some clients, some workstations to be connected by a server, and they named everything 3 this or 3 that. So soon after my arrival at UH, I ran into Norm and I was thinking of asking him about some research project. He says, how would you like to put together a bunch of networking equipment? So I said, I know nothing about it. He said, you've come to the right place. So, because 3Com had donated 1 copy of each of these 3 stations and 3 servers, and me and a bunch of graduate students, we put it together, got it working. And it was quite possibly the first local area network in the state of Hawaii. And you notice that the internet is a little bit far, not yet connected. We were not on internet as we know it today, okay? So, but you know what is interesting is 3Com in its last iteration was located right down the street here at the intersection of 237 and Great America, which is where Marvell is today. And over time, their products got commoditized, and they got bought by HP. And that was the end of the story. However, in a very strange twist now, Xerox is trying to buy HP. Not HPE, but the HPQ, the other business. It's a full circle now. The next interesting project I did with Norm was, and unlike the previous project, I sort of became the de facto project manager here. There was a company out in the Midwest. They were building satellite earth stations with the auto-acquired dishes and all, and they had donated 1 such dish to Norm, and he asked me if he would like to assemble it. I had no idea what I was doing, and this is a very interesting project. I don't think we'll have enough time to talk about it, but you know it had many problems. This is the first satellite earth station they had put together, the company. So there were some missing parts, which is a first order problem. There were some extra parts, which is the second order problem. We had no idea what we were doing. And one more thing, we have the dean here, he's a civil engineer. We never did the civil engineering work. The 6-meter dish, 20 feet in diameter, on top of engineering building, perennially windy, it cuts a lot of wind. I don't think we did the adequate foundation work. You can see that there are some ropes holding it together. Okay, and anyway, until my stay at UH, I was sort of like the station manager. At one time, there was some problem with the public television station. In fact, the entire PBS broadcasting for the state was going through this. And I think that satellite dish has been taken down since. But these projects, I learned a lot. I'm a 20-plus year veteran of the satellite industry now. I've seen hundreds of satellite Earth stations all over the world, from Siberia to sub-Saharan Africa, Asia, US. But this is where it all began for me. And we were slowly building towards the last project we worked on. And I was hoping that he would describe that in detail so I don't have to talk about it, which I'm not going to talk about much anyway, because I'm afraid that JJ is going to hit the buzzer now. Spread Aloha multiple access, he already talked about it. I'm just putting up this slide to introduce a few terms which I may need to use later. Basically, the idea was this is an interference limited channel. He made some very nice assumptions and obtained a very elegant, simple result. So simple even I could understand it. But the simplicity, and it was simple, but somebody had to do it and show it to you. Then you say, okay, it is simple. And it was that innovative and groundbreaking. And we all know about the power limitations. The one thing I wanted to point out is that in the satellite context, the remote terminals are not actually hurting for AC power. They have the power. But unfortunately, if you have a 1.2 meter dish, there is this FCC, You cannot transmit as much power as you want. So there is power limitation for them. Of course, spread Aloha multiple access is where, each bit is spread with only one sequence, as he pointed out to you, good autocorrelation properties. And the spreading was done to achieve multiple access here. And so each bit is spread into chips. So we could call this a chip slotted Aloha channel. Okay? And based on this idea, we started a company here, Norm started this called Aloha Networks. And the business model was to build a satellite-based internet access, low-cost internet access. And the secrets, of course, at that time, a lot of money was pouring into various forms of ISPs. It was the .com boom period. The secret sauce to the company was how to build a hub which will take all these time overlapping signals coming from hundreds, possibly thousands of users, decode them error-free into identifiable sequences. And with the state of the art, then we were able to actually achieve that and demonstrate the proof of concept. And as you know, the whole idea after that is to build nice looking remote terminal units. If I had a whole afternoon, I could count all the company who spent so much time and resource trying to build those remote terminal units, the CPEs. Unfortunately, it takes almost all the resources and money because the remote terminal units or CPEs have to be small, they have to be sexy, they have to be obviously low power devices. That usually bankrupts most of the companies. There is simply not enough funding. Unfortunately, I could not find a picture of our RTUs, so I thought maybe I will quickly show a photo of some of our personnel here. Actually, there are only, I believe, besides me and Norm, nobody else is here. I just wanted to point out, since we are here to memorialize people, that is Karen Withington, daughter of Norm and Joe. She worked with us. Sadly, she is not with us, but we remember her. She's definitely part of our Aloha family. So eventually, Aloha Networks ran out of money. And so I'm going to end it there. So of course, this has been mentioned by previous speakers. Aloha was definitely the reason which many very popular standards like 802.3, Ethernet, 802.11, Wi-Fi, 802.16, WiMAX, all those wireless technologies, and DOCSIS was mentioned. They all owe their origin to Aloha. And now, of course, there is a lot of, there is talk about enhanced spectrum Aloha. Initially, the ESSA was brandied about in the satellite context, but now it is being mentioned for all the channels. And now, today, of course, there's Internet of Things. This is a classic, Aloha-like situation. You have a large number of geographically separated, uncoordinated users sending data in a low duty cycle, and they all have power limitation. They're running off of batteries. So, this is some of these ideas, even though they are old wine in a new bottle, they owe their origin to Aloha. And this has, what I wanted to comment here is that the way the IoT is interpreted now and the way it is going to evolve is going to start encompassing a lot more things in its purview than we think it is today. And of course, any discussion about the new channels cannot be complete without discussing the elephant in the room, which is 5G. But when I talk about 5G, I mean both fixed and wireless. There is a lot there. And both of them are going to really make a huge impact in our channel. And 5G, of course, everybody knows about what is happening, and I'm not going to talk too much about it. But 5G, collectively, both of them, going to have so much disruption in so many sectors. It's unprecedented. We will have healthcare, manufacturing, automotive, retail, and entertainment. Did I mention entertainment? Okay. So entertainment is going to, basically they are all related. Entertainment is going to influence, this is a closed loop. All of the above. There are a bunch of millions of people consuming advertisement and influencing all the channels, all the other sectors of population. And there is a lot of new bandwidth being promised for 5G, but I got bad news. I think all of that has been spoken for. Almost all of that is going to be full of entertainment. If I stood here and 10 years ago I told you that there will be a couple of thousand people sitting in an arena watching esports, which is nothing but 2,000 people sitting and watching 5 guys playing Grand Theft Auto. And actually they bought tickets to go there. That's even more shocking. And but that's happening. And while they're watching, they're all texting their friends, going on Instagram. That is how big it is. So entertainment is actually the biggest of the elephants in that herd. And that is going to greatly influence the utilization of the channel. Why I meant was that we already spoken for all the new bandwidths coming. So all the future work will have to incorporate how we can squeeze more out of it. And that is where because you see already the younger generation is walking like this. Okay? 5 years from now, everybody will be walking like this. There's nothing more left. Maybe half of us will go blind by then. So this is where, in order to squeeze more out of the channel, each new sector is going to pose unique challenges and opportunities. And we, at this point in time, perhaps will have to re-examine the assumptions based on which we got our original results to see what we can do to make the channels more efficient. I think I'm almost out of time, so I'm just going to end it here and say thank you very much.
The goal of my presentation this morning is just to review very quickly the result of the research activity we have done inspired by Aloha system that we have done at Politecnico di Milano in the last 4 decades, so a long span. At Politecnico, at the beginning of the 70s, I started a lab, Advanced Network Technology Lab, that started studying the problem on the design and optimization packet switching network. We are still, this lab is still alive, and we have in this year changed topic to topic according to the most relevant themes in the networking. So one of these is the multiple access protocol. And we have been active for quite a while. In 1978, I was inspired by the Aloha protocol, not only because of this originality and simplicity, as Norman has recalled just now, but also because of the beauty of the environment where it was developed. So I enjoyed very much my visiting professor position at University of Hawaii, and I have a good memory of the time I spent with Norman discussing research topics while we were surfing. I think you remember, Norman. Working hard in the morning, a long lunch break, not for food, but for swimming and surfing, and then go back to the office late in the evening. So it was very enjoyable time. So since then, we have studied the problem of multiple access related to, derived from the Aloha at Politecnico di Milano, and these are the people that have helped to produce the result that I'm trying to go into review. This is a span of 40 years, starting from the black and white picture on the top to the youngest faculty at the bottom. So if you search on the IEEE Explore and ask for the papers that mention the Aloha name in the title, you end up with a list of about 3,000 papers. So that means that a lot of activity in these old years, and this result is a kind of jungle of the many different protocol proposed, analysis, and so on. So I'm suggesting to use this kind of a tree structure where the root is done by formed by the Aloha. There is a branch collecting all the protocol that has been derived, like the reservation Aloha, frame Aloha, tree algorithm, and so on. Another branch is specify the different environment where this protocol can be utilized: satellite, cellular, vehicular. And the last one is where all the analyses have been done, most of them regarding the stability, the throughput, and delay of the Aloha. So, following this scheme, I will start from presenting the protocol that we have developed in Milano very quickly. A reservation upon collision was proposed for satellite, and is a variation of the reservation Aloha. The packet is transmitted in a slot, and after a slot there are n mini slots which are used for orthogonal signaling. According to this information, you can build up a time division multiple access scheme which achieve a full capacity, of course ignoring the overhead due to the mini slot. So to accurate evaluation of the throughput, you have to account this overhead, which of course increases with the number of n. Collision resolution based on echo, we propose for a satellite and cellular environment, and in this case, the time slot where packets are transmitted are longer than the packet length, and we allow a station to start the transmission within the slot at random. This allows, when a collision occurs, that stations which are involved in the collision can recognize which is the first station and which is the last station in the collision. So we get an information that allows us to build up a ternary collision resolution algorithm whose throughput goes up to 2/3 in terms of slot. Here again, the slot is longer than the packet transmission time, so there is an overhead that you have to pay. And according how do you implement it, you can evaluate the actual efficiency. Capture division packetized access, we propose for cellular system where no boundary reuse technique is enforced. So in this case, to cope with the intercell collision, we can exploit the capture. So the ability to recognize one signal among several that have been transmitted at the same time. We use a kind of polling system within the cell, and when a collision occurs and is not resolved by capture, we retransmit the packet. The performance shows to be very, very attractive due to the fact that we don't waste bandwidth a priori, but we just waste bandwidth performing a retransmission when the collision has occurred. Centralized packet reservation multiple access is a kind of centralized scheduling mechanism which integrate the traffic of different characteristics and requirements. That's for cellular system, and it uses SLR as an access and reservation channel. And we have shown that this protocol is very suited to integrate different kinds of traffic like voice and data. Reliable reservation Aloha is a kind of dynamic TDMA that we have proposed for vehicular communication. Here, the dynamic reservation are made through the reservation Aloha, and the status of the channel as seen by each station is propagated to ops ahead in order to avoid intercell collision. This protocol was shown to provide a very useful, reliable point-to-point and broadcast services. This is the last protocol that we have suggested, and it refers to the environment of RFID. In this case, typically there are n stations that need to transmit one packet. We can use the frame Aloha protocol, which provides, as usual, the 1 over E throughput as maximum, but according to our suggestion, by exploiting an initial station grouping mechanism, you can achieve much higher throughput. So the resulting Aloha in smaller group increases the throughput up to a value which is very close to the best, the throughput that you can get with the best 3 protocol, as was suggested by Gallagher and Tsibakov. These are the proposal of new protocol. We have done also some analysis, so we go to the branch on the right, and the analysis that we have performed in this year, at the beginning of the 80s, we studied the performance of slotted Aloha with the variable packet length. Now, we expect in this case that the performance get worse, because the longer the packet, the longer is the higher is the collision probability. And in fact, it was, our analysis proved these results. In cellular system, when a collision occurs, we have some impulsive noise. So this impulsive noise can be taken into account by techniques like TDMA, CDMA, or forward error correcting codes, but also just simply by retransmission. So the analysis have shown that using retransmission, which meaning that you pay overhead only after a collision has occurred, it provides better performance. The throughput analysis of the standard IEEE 802.11 was published in this paper of year 2000. The results were obtained assuming that interference stations are considered stationary and independent. And the results show a very good matching with the simulation. It was a very successful paper which received more than 10,000 citations. This contribution to the analysis is regarding the RFID environment, and if we know if the number of tags, the number of stations involved are known, it turns out that the frame length, that setting the frame length equal to backlog size at any frame is the optimum policy, and you achieve the throughput equal to 1 over E. So these are our contribution to the 3,000 paper, or even much more, that have been published up to year, let's say, 2016. So after so many years that Aloha has been studied, and after so many published papers, a question that arises is that there are still any missing problem, any missing issue about Aloha? And the answer is yes. If we consider, we are considering now the channel without feedback, meaning the case where no other protocol except Aloha can be used. We see that there were some missing problem in the literature regarding the Aloha stable operation, the maximum throughput, and the performance. So we have done some work to fill up this gap. So regarding the Aloha stability, a well-known result in the literature is that the transmission probability is constant, the system is unstable. And also it's unstable when n become very large if transmission and retransmission occur at different probability. It was a result from Gelenbe that is not here today, unfortunately. And it was recognized in the beginning that in order to achieve stability, transmission probability must be reduced at any attempt. And in fact, in the Ethernet, in the 1976, in the standard was introduced the binary exponential backoff. The exponential backoff can be also considered in a more general form, like shown here, where the probability to transmit after the attempt I is B, where B is not necessarily equal to 2, to the minus I0, where I0 is the delay for the first transmission. So we have studied this system, assuming a general model where there are n stations involved in the transmission. Each one is characterized by the Q length and the backoff index. The resulting Markov chain is too complex to be studied, so we have simplified, assuming that all Q are full, meaning that we assume the worst case of the system. So we have only one parameter per station, the backoff index. Studying this Markov chain, we found the stability condition, new stability condition, and this is the, which are summarized here, that the system is stable, meaning that the chain is a positive recurrent, if and only if the B is greater than 1 and I0 is greater than 1. In all other cases, the system is unstable, either null recurrent or non-recurrent. And it's worthy to mention that also internet, if there is no limit on the number of transmission, turns out to be unstable. These are very recent paper, and one is not yet been published. It will be soon appear on the transaction information theory. So it's very recent results. Regarding throughput, in the literature, the existing results have been obtained considering that interference stations are stationary and independent. And the maximum throughput achieved is 1/e. We got new results, assuming the model that I showed you for the stability, and we solved the Markov chain by numerical solution, and we have validated the result by simulation. Regarding throughput, I summarized in this table some of the value, meaning that the last line represent the throughput 1/e obtained with the statistically independent interference station. But we show that if we set suitable value for I0 and B, we can get a throughput which is higher than 1/e. This is because you can observe in the system that there are some temporary capture from the station. So this increases the throughput, but also introduce a higher variability in the delay. So you have to be careful, not just consider the throughput, but associate the throughput with the corresponding delay. So we have done some analysis on the access delay, and of course the average value is simply obtained by the little result, and is equal n number of stations divided by the throughput. But the access delay cumulative distribution functions, as is shown in this graph, it is a heavy tail, so meaning that the delay has a large variability. To study the variability of this delay, we have considered the variance of the access delay, and we found the condition under which the variance is finite. Here is shown in this graph, in the plane, number of stations on the y-axis and the I0 in the x-axis. For each value of B, here I've shown two curves, B equal 2 on the left and B equal 135 in the right. And for this curve represents the boundary, so the area, the set of value n and I0 below the curve correspond to a variance, a value of the variance finite. Above is infinite, so it means that is a stable the system. So this shows that if we look at this picture and we look the value for I0 small, we see that the number of stations for stability is very low, so it's unpractical. And if we increase I0, we increase the number of stations that we can allow in the system, which is nice, but we suffer a larger first access delay. So there is a trade-off to be considered. So these are the results that fill up the gap that we found in the literature. And, but there are still, if you want, regarding the backoff in general, a few other issues open. If we consider a different law, different from exponential. For instance, polynomial backoff law. which is characterized as shown here by the two parameters A and K. And there are some guesses that have not been proved. So there is some still new problem for young and PhD students that I don't see so many here, but I'm sure that we have connection with them, so we can suggest this problem. So the guess that should be proved is that the polynomial Beckhoff law are always stable if A greater than 1. The access delay moment always exists, and also investigate how the throughput changes over the parameter A and K. We expect also that as K decreases, the response time to congestion become larger. So these are some issues regarding the specific problem of the Beckhoff in Aloha that I'm sure, together with other problems that will be arise maybe this afternoon, the other talk, may show that in spite of so much activity on Aloha, there are still something to find out at this time to complete. So what I'm looking for is that this problem will be solved pretty soon, and so we will be able to call a next meeting, a next conference on Aloha like today, pretty soon. So thank you very much, and Aloha everybody.
We have time for some questions and answers, and we'll pass the microphones, and then our three speakers can come and take one of the, yeah.
Hi. I was intrigued by the observation of a stadium full of people all watching the same video game going on. And I note that within the last couple of days, a massive bang bang shoot 'em up game, Call of Duty, was released, and there's a million people downloading 100 gigabyte images. My observation on Aloha is how much of our thinking has been colored, shaped over these last 50 years by the thought of using a many-to-many system to achieve what looks like one-to-one, but many of them overlaid, when the underlying mechanism also supports one-to-many, which would serve this much newer use, which we're seeing on the internet today. I'm just commenting that I'm just wondering how much our thinking has been looking in, well, there's another field where you can go look at. Yeah, that's the end of my observation and question.
Hello. Well, actually, all those channels I pointed out, all the market segments that 5G, IoT, everything is going to affect. If you look at each individual sectors, each one of them is an ecosystem of channels with their unique problems, you know. So, sure, I mean, initially we started off as a universe with a bunch of point-to-point channels. Then it was always one-to-many channels. Then after Aloha, we have better understanding of the return channels. But in reality, they are all hybrid channels, all of them. And of course, I mean, we both seem to have arrived at one conclusion. For the future, we will have to consider feedback in order to optimize. And if you, even though initially, for instance, IoT started off as a UDP, you know, but now I'm personally aware of at least 2 or 3 startup companies where the peel and stick IoT devices, they all come with cellular capability. So they have everything, cellular, Bluetooth, long range, and of course, Wi-Fi. So everybody is doing everything simultaneously, and those will be the challenges that we may have to work on for future.
Thank you.
Other questions? Back there?
Yeah, and okay, absolutely, that was a collision. From all the presentation I gathered, maybe I missed something, and correct me if I'm wrong, that all the traffic here seemed to be homogeneous. That is, all the terminals, all the sources are bursty traffic, and they don't really care, don't put any value on the delay until they actually successfully send their packets. There was a big thing in the internet over a year, which is the quality of service. What is the status right now of integrating different classes of traffic? Some of them bursty, some of them longer burst, some of them require very quick response, some of them can take errors that the packet doesn't arrive, etc., and some don't. Kind of integrated Aloha system, let's call it.
Which, I'm sorry. Yeah, that's for sure a problem that you mentioned. But I'm sorry, I'm not aware of any kind of solution to your question. I don't know. You want to answer or any other comments?
Well, addressing some of what you've said is the POTA scheme that was synthesized on the SATNet project, priority-oriented demand assignment, which was tried to be everything for everyone. It assumed that processing power was going to be very cheap, and so there was no problem in scheduling and rearranging and doing all sorts of things. And the title of that protocol is priority-oriented demand assignment. So the distributed queues or central queues prioritized, and traffic indicated their different quality of service that they needed. I don't know, well, we implemented some of that before the SATNet project ended. I don't know if any of that has actually found its way into the real world. Probably has.
Just wanted to make a very quick comment. Most of the time, the quality of service is addressed by throwing more bandwidth at it. That is what has happened. However, the other way to look at it is this. Most of the real-time applications that need to be addressed right away, they tend to be a little bit more robust. Whereas the TCP/IP guarantees error-free delivery. Okay, so you keep trying until you get through. So that is how it has happened. But eventually, every user, if you are persistent enough, get what you want. Maybe unhappy, but you do.
There were questions. Oh, there was a question back there.
Okay, Michael Usher, UCSC. I have a history question, probably for Richard Binder. The early description of Aloha focuses on the terminal to host connections, client to server. And then there was a mention of the interconnect of the T1 bearer channel for interconnecting to another network. I'm just wondering, there's kind of two questions in one. How did the early discussion about host-to-host communication evolve in the Aloha project? And what about inter-network addressing? I just wonder if resources were directly connected, or was it through a gateway mechanism?
Well, I'm not aware of any host-to-host discussions while I was involved in the Aloha project, since we only really had one host when we built the initial system. And we added other hosts, but they were all just other resources for our terminal users to talk to. What was the last part of your question again?
Well, when you introduce the satellite connection connecting Aloha to ARPANET, that would imply that terminal resources within Aloha now could connect directly to resources within the ARPANET. And so that requires an addressing. If you're going to connect directly, your addressing is introduced,
Sure.
and it also means that you now start to get to a real internetwork rather than a gateway.
Yeah, and it might have slid by when I said it earlier, but the second version of the Mini-Uni, which was reprogrammed with a gateway in it to allow users to connect all these different resources, since AlohaNet packets only had one address, the source address in it, didn't have a destination address in the packet. We had to do it through a manual connection table setup in the Mini-Uni. So the user would type some characters that told the Mini-Uni, I want to connect to that resource, and then it would proceed to talk to that resource until it was finished.